Welcome to the second part of the nucleation morphology and reactor type chapter under the head of emulsion polymerization. Now, we discussed about the particle nucleation and we started the particle morphology in the previous lecture. In this lecture, we will continue this particle morphology concept. Apart from this, we will discuss about the various type of reactors involved for the emulsion polymerization, and we will perform the performance study of emulsion polymerization reactor. Now, just a brief overlook that what we discussed in the previous lecture, that we were at the phase of particle morphology. Now, when there was a separation in the polymerization process, this can be found in the different regions like cluster as well as in the polymer matrix, and we talked about the thermodynamic imbalance which intend to develop during the course of this polymerization, and subsequently it may increase the free energy. Therefore, there may be a chances of polymer migration towards the equilibrium morphology, and this may create several issues. Now, this polymer migration, this results to increase in the size of the cluster. This may be due to the polymerization within the cluster, diffusion of polymer into the cluster, coagulation with other clusters. Now, let me give you a brief outline about this, because if you see that we have formed one hollow network where the things are attacked with respect to, and then there was a starting of polymerization, and this cluster become more and more bigger in size, and then the polymer migration took place. So, then these developed polymer sites over the cluster may intend to form the further polymerization within this cluster. Then there may may be chance that the polymer particle may get diffused into the cluster, and then they may be formed, that there may be chances that they may form the coagulation with the other cluster. So, these are the several issues related to this particle morphology. So, whenever any of these three situation occurs, then there may be a change in the morphological segments of these polymer particles. Now, usually when we talk about the migration, then question arises that who tutored this migration. So, this migration is basically tutored by two interfacial forces. One is that is the van der Waals force of attraction and repulsion. These are usually very weak forces. Then second is the resistance to flow that arises from the viscous drag. Now, these van der Waals forces between the cluster always try to attract each other. So, that is one of the reason why this migration is tutored. However, these van der Waals forces between the cluster and aqueous phase, this is the cluster and the aqueous phase, this can be attractive, which will try to shift the cluster towards the surface of the particle, and sometimes to be repulsive. So, this moves the cluster towards the center of the polymer particle. Now, these van der Waals forces they are proportional to the interfacial tension, and this interfacial tension is again a very important role in the migration tendency. Now, if the interval viscosity of the particles are high, then metastable morphology will be obtained. Now, this low interfacial tension will promote the grafting reaction. So, if you are intended to perform this grafting aspect, then it is a very useful platform. Now, on the other hand, if for the case of particles with the low internal viscosity, equilibrium morphology can be achieved. So, the polymer obtained, this could be the highly unstable due to the large interfacial surface tension, which may lead to increase the van der Waals forces. So, the process time for such system will also be very long because of this involvement of weak van der Waals forces. Now, let us have a look about the emulsion polymerization reactor, that is the next segment of our chapter. Now, these emulsion polymerization are used in wide variety of applications like paint, coating, paper coating, adhesive, carpet backing, leather treatment, additives for textile and the construction material, impact modifiers for plastics, biomedical applications, etc. So, they are having very wide spectrum of uses. Now, here you see that we have represented emulsion polymerization reactor. This is for the production of polyethylene. Here the ethylene is subjected to this primary compressor and secondary compressor, and then there are two stage side feeding where the peroxide, these are the initiators, so and peroxides are added to these different reactor zones. Now, there is a subsequent addition of the coolant, because you know that these reactions are some sort of exothermic in nature, and if we do not add these coolant, then there may be a chance of a thermodynamic imbalance which may create a further issues. So, these are the three zones. I am not going to detail about these zones related to the things, but the thing is that this is a typical type of polymerization process reactor. Here you may have several coolers. This may tend to reduce the temperature, then high pressure separators, then here you are having certain wax separators, etc. So, these are the some certain side products and byproducts. Now, each of these reactor or each of these zones, they require a particular microstructure analysis and a different production rate, and that is why you see there are different side feed zones. Now, secondly, the emulsion polymers, they are product by process whose microstructure is determined in the reactor. Now, there are certain prerequisites or certain requisite aspect for these emulsion polymerization reactor. Now, these are that they should allow the fine tuning of polymer microstructure, that is quite obvious. They should be useful to prepare many different grades in the same reactor, and they should be adaptable to a wide range of production rates. So, these are the certain requisite aspect for these emulsion polymerization reactors. Now, these reactors either can be batch type, semi-continuous or CSTR. Now, semi-continuous stirred tank reactor is the most widely used reactor for this emulsion polymerization process. Now, for obtaining very large capacities, a small number of grades batteries of CSTR are also being used, but due to certain limitations of the process or process requirement, the batch reactors are less frequently or rarely used. Now, tubular reactor are also less popular, and only continuous loop reactors are usually used in the commercial approaches. Now, let us have a look about the semi-continuous stirred tank reactor. This process we have already discussed in the previous lecture. Now, this is you see that this is a solvent and surfactant, then these are the semi-continuous batches, and you may find different polymers having the different number average and weight average molecular weight. Now, the reason behind the wide acceptability of these reactor is the great flexibility towards the reaction parameters. You know that we have already discussed the various reaction parameters, those who are involved in the emulsion polymerization process. So, this type of a configuration, semi-continuous type of a configuration, offer a great flexibility with respect to all those parameters, and that is why, because of this particular governing factor, these reactors are found themselves, or they are the very good candidate for performing this emulsion polymerization process. The reaction temperature and the polymer composition in the feed can be adjusted depending upon the composition and the volume of the initial charge. And second aspect in this category is the composition and flow rate of the feed. The major limitation in this operation mode is the comparatively low productivity. So that is you can say that this one is disadvantage, a slight disadvantage of this particular process. Now various commercial need polymers, they are manageable through these reactors as they allow the modification of various unique polymer properties, such as sometimes you may require the copolymer composition to be addressed as per your need. You may require molecular weight distribution approach, you may require different polymer architecture, you may require different particle morphology and a particle size distribution. So based on your requirement, this particular approach offer a better candidacy. Now next is your CSTR, that is the continuous stirred tank reactor. Now this CSTRs, they always grab attention due to the capabilities related to providing the product in a large scale. They have a broad residence time distribution, and sometimes in the reaction engineering term referred as RTD, and that is why they are obtaining a narrow particle size distribution in single CSTR. That is the quite tough. Now incorporating the multiple CSTR in series, this can help to overcome that particular issue with the particle size distribution, because this helps in effective heat removal and narrow residence time distribution inside the reactor. This will lead to obtain narrow particle size distribution. Now you can see this is the multiple CSTR in the series. Here you are having this initial concentration of your reactant, then the output of this reactor is the input of second reactor, and then the output of your second reactor is the input of your second reactor, the subsequent reactor. So you can have n number of reactors in series to get the final product in this concentration. Now in fact the commercially it is not at all feasible to incorporate a large CSTR, because the various complexity may involved in due course of time, and that is attributed to the great transition, etc. Therefore, the use of multiple CSTR as reflected in this figure is quite beneficial in the practical approaches. Now during the polymerization in CSTR, it very likely that intermittent nucleation may occur, which results the formation of multimodal particle size distribution. Now sometimes we need to overcome such type of issue. The tubular reactors usually are employed before the CSTR in this polymerization process. These reactors, they help in the smoothing the particle formulation. So you may have a combination of different type of reactor to achieve the desired goal. Now due to the uniform mixing inside the reactor, the copolymer composition sometimes remain constant throughout, and you may need to perform certain manipulation in this approach. So the manipulating the intermediate feed to the monomer, this can also help to control the copolymer composition and molecular weight, because both the things are extremely important to carry out the desired product formation. Incorporating the multiple CSTRs, they provide another advantage of distribution of average residence time among each CSTR attached in the series. So this will increase the flexibility of the reaction. So therefore, based on this, the production of variety of specialty emulsion polymerization product in a single setup can be possible. So they offer more and more flexibility. Maybe you can use the multiple reactor in combination, you can have a different reactor in series. So by this permutation and combination, you can achieve your desired product parameters. Now let us have a brief look about the tubular reactor. Now the tubular reactor, they provide very large surface to volume ratio as compared to the other reactors. Now due to this, very high conversion can be achieved in a small volume. Therefore, the size of reactor, the installation space, these can be significantly reduced, and economy of your process can be improvised. Secondly, these reactors have quite simple mechanical design, and they can perform the efficient heat removal. So, due to their compact design, sometimes they found to be quite economical. Now, this is one of the example of the tubular reactor. Here you see that we are feeding the monomer, we are having the initiator, we are having the solvent, they all together mixed in a mixture, and subsequently they are pumped to this tubular reactor where they are performing the formal reaction to get the the polymeric product in the form of a solution. Now, here at this stage you can introduce the inhibitor, so that you can truncate the further polymerization reaction, so that you can control the PSD, particle size distribution, you can maintain the appropriate molecular weight distribution, and by this way you can collect your polymer. So, this is a typical design or typical layout of a tubular reactor. Now, various tubular reactors are being used commercially, they are quite common. Now, some of them we have already listed, like a single pass tubular reactor, pulsed column reactor, Cotte-Taylor flow reactors, the Wicker type of a reactor, the loop reactor. Now, single pass tubular reactor, just have a brief look that what are the advantages and disadvantages associated with all these kind of reactors. The single pass tube reactor, they have limitations related to weak mixing, which sometimes result to the phase splitting of the polymer, and sometimes it may create a problem in the final product morphology. The pulsed tubular reactor can overcome this particular limitation which is associated with the single pass tube reactor. Now, this is attributed due to the involvement of sieve plates, stocked Raschig rings inside these reactors, so that they can remove all those splitted particles in due course of time. Now, these obstacles sometimes result into the great pressure drop, as well as the chances of a coagulation. This the coagulation sometimes increases to a great extent. So, this is one of the disadvantage associated with this pulsed tubular reactor. And because of this coagulation approach, the cleaning and proper reinstallation of these reactor are extremely difficult, or sometimes it is very tough and cumbersome in this approach. Now, this is a typical figure of pulsed tubular reactor. You can see this is the tubular reactor. Here you are feeding the different ingredients to this reactor, and you are having the outlet of this one. You may have a feeding tank, rotameter, impeller, premixers, preheaters, etc. Now, the Cotte-Taylor type of a flow reactor, this is another category in this series which it consists of two concentric cylinders. The immovable outer cylinder is usually fixed and jacketed for efficient heat transfer, while the inner cylinder rotates to its axis. Sometimes the samples is placed between the cylinders, and under particular operating condition the counter rotating toroidal vortices are formed. So, the mechanism of Cotte-Taylor flow is similar to the multiple CSTR in series, and this makes the residence time distribution in these reactors similar. So, this is one of the added benefit. Now, here you see this is the typical diagram of Cotte-Taylor flow reactor. You see that there are two cylinders, one is this is the inner cylinder and this one is the outer cylinder, and the fluid is just rotating like this. Similarly, now here in a larger spectrum you see that this is the Taylor-Cotte cell. Now, here this is the inner cylinder and this is the outer one, and you see there are different vortices being formed in this particular cell to facilitate the polymerization reaction. Now, during the polymerization, the Taylor number is prone to change inside the reactor due to the change in the viscosity of the solution in a linear direction. So, it is quite evident from this particular figure. Now, as the viscosity change follows a particular trend, the Taylor number can be managed by modifying the cylindrical outer cylinder with the conical one. So, this can counteract the viscosity increase factor, because again viscosity plays a vital role. Sometimes if it increases drastically, then the process may get hampered in due course of time. So, therefore, this is one of the major way through which you can counteract the viscosity increase factor. One factor that induce the coagulation is the gravity induced phase separation, that is the creaming, sometimes referred as a creaming. So, the Vickers reactor configuration is found to be quite useful to overcome such type of issue. Now, the tube meanders between the fixed cylinder supports, this is the integral part of the Vickers reactor. Now, the tubes moves in such a manner that it develops the huge number of curves in the parameter of the cylindrical supports while maintaining the curvature. Now, these tubes are coiled from the bottom to the upper part of support. Now, these type of reactors are newly modeled configuration that is found to be an effective solution of coagulation related issues in the emulsion polymerization. However, because of the complexity in nature, there is no practical application commercially has been made as on date for these type of reactor. Another form of reactor is the continuous loop reactor. These can be said as the modified and improved version of CSTR in emulsion polymerization. Now, it consists of a tubular loop that connects the inlet and outlet of the recycle pump. Now, these reactors have high surface to volume ratio as compared to the conventional CSTR, and that allows very high conversion and shorter residence time. So, these reactors provide a greater flexibility and minimum losses during the polymerization. Therefore, it offers a good economy related to the other available configurations. Now, here you see that this is the continuous loop reactor. You see different loops are there, and this styrene and initiator, they are pumped with this the recirculation pump, and you may have the other zone for the styrene, and this one is butadiene. So, you may have the styrene butadiene rubber at this outlet. Now, these reactors are bound with several limitations, although they offer a very good flexibility, but they are having certain limitations. The core shell particles cannot be produced inside these reactors, and it is difficult to adjust the particle size distribution and obtain the smaller particle. Large amount of surfactant is usually required, and the separation of those surfactants sometimes very tedious job from the developed or produced polymer mass. And second aspect is that the feed should mechanically stable to prevent the shear induced coagulation. Sometimes it is quite difficult to maintain this stability issue in the reaction aspect. Sometimes another disadvantage is that the intermittent nucleation may occur, that may promote the further or the parallel polymerization. Now, this process is new, and very limited information is available regarding these reactors, and sometimes the more technical information is available to various research labs. So, therefore, its application is restricted to the manufacturing of homopolymer and copolymer of vinyl acetate. Now, let us have a look about the performance of emulsion polymerization reactors. Now, we can conclude that only CSTRs and loop reactors have found attention for commercial applications. Now, these reactors are designed to provide the efficient mixing. The modeling, this includes the macroscopic balance by considering the reactor as a whole. So, these the inlet and outlet streams, they are included in the balances for generalization of the model. For batch reactor, both terms, that is inlet and outlet stream, this can be neglected. For semi batch reactor, outlet flow term can be neglected for designing aspect. Now let's have a look about the performance related equations. So we can write the mass balance equation. The mass balance for any species can be written as dNi over dt is equal to Fi in, that is in, and Fi out plus Ri V. Now where Ni is the amount of a compound I in the reactor, that is having the unit of mole. Now Fi in is the inlet molar flow rate of component I, that is represented as mole per second, and Fi out is the outlet molar flow rate, that is again represented as mole per second. Now Ri is the net generation of I in the reactor, and that is having the unit of a mole per liter second, and obviously the V is the reactor volume. Now this equation applies for the monomer, initiator, water, emulsifier, and moles of each monomer incorporated into the polymer. This also applies to the number of polymer particles, precursors particle, and the moments of molecular weight distribution. So usually the polymerization rate of a monomer J is expressed as the rate of a monomer consumption RPJ, and therefore this RMJ and is equal to minus RPJ. So when we talk about the continuous operation, this Fi out can be calculated as Q out upon Ni over V. Now Q out is the volumetric outlet flow, V is the constant in the continuous operation. This is represented by the volume of reactor. Now in emulsion polymerization, the density of a reaction medium does not change significantly. Therefore, the volumetric inlet and outlet flow rate can be considered to be the same. Now when we talk about the performance equation, then we need the heat balance concept. So energy balance equation can be written as summation I and I and Wi Cpi dt over dt is equal to summation J RPJ and delta HR, that is the heat of a reaction volume, then summation I Fi in and Cpi in Wi T minus Te plus Q removal plus Q loss plus Q stirring. Now here Cpi this and Cpi in, this is in kilojoule per kilogram per Kelvin. They are the heat capacities of the compound I in the reactor at the entry condition respectively. Now delta HR is the polymerization heat of a monomer J at the reactor conditions, that is represented as a kilojoule per mole. Now T is the reactor temperature in Kelvin, Te is the temperature of the feed, that is in Kelvin. Q loss is the heat losses to the surrounding, that is through the reactor lid. Q stirring is the heat produced by the agitator, it is having the unit of kilojoule per second. And Q removal is the heat removed through the heat removal devices, cooling jacket, etc. You recall that in the figures we always introduced either cooling fluid or cooling water inside the reactors. So for heat removal through the cooling jacket, that is Q removal is given by minus U AW delta T ml. Now U is the overall heat transfer coefficient having the unit of kilojoule per meter square second Kelvin, and AW, here this AW is the total heat transfer area in meter square, and delta T ml, this is the logarithmic mean temperature difference between the cooling fluid and the reaction media. Now it is given by delta T ml is equal to T minus T in minus T upon T J out upon ln T minus Tj in minus Tj out. So Tj in and T out are the inlet temperature, inlet and outlet temperature of the cooling fluid in the jacket. So we know that the several resistances play a vital role in defining the heat transfer coefficient, such as the resistance due to the diffusion, mass transfer, chemical reaction. So for this case, the internal resistance usually controls the rate of heat transfer. Now the internal heat transfer coefficient usually a function of impeller type and dimension, sometimes impeller speed, reactor diameter, physical properties of the reaction mixture. So, it can be calculated by means of empirical correlation based on the dimensionless groups. The practical method for determining the heat transfer through any cooling device is to measure the flow rate and the inlet and outlet temperature of the cooling fluid. So, you can represent the Q removal, that is MWCP T in minus T out. There this MW is the mass flow rate having the unit of kilogram per second. Now, these equation allow the estimation of polymerization rate from temperature measurement. Now, reaction calorimetry is the tool to determine the internal heat transfer. It is an influential non-invasive online monitoring technique and measures the amount of energy released or absorbed by a chemical reaction. So, during online monitoring, heat flux sensors are installed on the wall of the reactor vessel that directly measures the heat across the reactor. So, in this particular lecture, we discussed about the remaining aspect of emulsion polymerization reactor, especially attributed to the morphology. Then we discussed about the performance of emulsion polymerization reactors with a due emphasis to all kinds of applicable reactor as on date. We discussed the merits and demerits of those reactors and where we can apply all those reactors. If you wish to have further studies related to these reactors, we have enlisted several references for your convenience. You can have a look of all those references for further studies. Thank you very much.